All right, so yesterday we finished up talking about nucleophile strength and how that correlates to solvents, but I did want to go back and talk about nucleophilicity in a little bit more detail, because nucleophilicity gets confused a lot with basicity because they behave a lot in the same way, right? So if we look in the definitions, a base grabs a proton, kicks off a leaving group, where a nucleophile attacks a carbon and kicks off a leaving group. In terms of the mechanism, very, very similar, right? So what we need to consider is how they're different. For a nucleophile, the thing that matters is the activation energy, right? How large that hump is that you have to overcome. So it has everything to do with EA, whereas basicity on the next page says that activation energy doesn't matter for acid-base reactions. What matters is how stable your product is compared to your starting material. So they're very different things. If we think about basicity, it's a measure of thermodynamics. If we think about nucleophilicity, it's a measure of kinetics, meaning how quickly something goes. And then I kind of overwhelmed you guys yesterday with a big discussion on solvents, and this kind of ties it in together into a nice summary. And what I like to do, if this doesn't make sense, is make kind of a general summary. And like I said, you can go to Master Organic Chemistry too if you need any help understanding this. But let's make a little summary table. So because I'm an organic chemist, my periodic table looks a lot like this. Everything else on the periodic table is just wasted space, right? All right. So we are primarily concerned with this top right-hand corner. And when we're looking at this, what I like to do is break it into different types of nucleophiles. So the first one is an anion nucleophile, and this is going to be in a polar aprotic solvent. And for an anionic nucleophile, meaning it has a negative charge, it gets more nucleophilic as you go left across the periodic table. So I'll write more nucleophilic as you go left. Sorry, I'm going to zoom out a bit. Does that make sense? So we know that fluoride with the negative charge is not a very good nucleophile because it's really stable, it's electronegative. But if we have something like a nitrogen with a negative charge, that's really unstable. It's not as electronegative, so it's going to be a great nucleophile. Yep. Anionic nucleophile, polar aprotic solvent. So an aprotic solvent, what does that mean again? No hydrogen bonding, right? So it's a solvent that can't hydrogen bond but is still polar, right? Okay. The next one we have is an anionic nucleophile. But this time we're in a polar protic solvent. So polar protic solvents, like we said, can H-bond, right? So polar protic solvents, same sort of thing as we go across a column from right to left, we get more nucleophilic. Solvent doesn't really play that much of a role when you're comparing things in a row, right? When does it matter? Up and down a column, right? Okay, so now let's think about this. All right, anionic nucleophiles, do they get more nucleophilic in protic solvents? Or sorry, let's back up. I need to be clear about this. Let's do the red one first. So an anionic nucleophile in a polar aprotic solvent, does it get more nucleophilic as you go down a column or up a column? What do you guys think? So polar aprotic, right? So aprotic means no H bonding, which means there's nothing stabilizing the nucleophile. It's just kind of a naked nucleophile. In this case, what's more stable, a fluoride with a negative charge or an iodide with a negative charge? Iodide, right? It's got the larger atomic radius. That means it gets more nucleophilic as you go up, right? Okay. Anionic nucleophiles and polar protic solvents, now we have to consider H bonding. If we have H bonding, that fluoride anion is going to be wrapped up by a bunch of hydrogen bonds. It's not going to be available to act as a nucleophile, right? So in this case, we actually get more nucleophilic as we go down. And then last but not least, we've got one last trend. And that is for polar protic nucleophiles. These are ones that are neutral. So I'll just write N-E-U-T-R-A-L. We'll spell it all out. And in this case, it still follows those green arrows, right? So the main thing to remember is nucleophile strength changes depending on the solvent that you're in when you're comparing columns, not in rows. I know this can be a bit overwhelming to learn, but the key thing is understanding why. H-bonding will wrap up charged species, and the smaller they are, the more tightly they're wrapped up. So they're not as available to act as nucleophiles anymore. Make sense? All right, so now what we need to do is we need to go back and we need to look at leaving groups a little bit, and that's what you guys were looking at with your pod. Leaving groups, luckily, are a heck of a lot easier than nucleophiles. So leaving groups. If we think about SN1 versus SN2 reactions, which reaction do you think relies on the leaving group more? Do you think it's going to be SN2 or SN1? SN1. Why SN1? Rate determining step, right? SN1 reaction, the rate determining step involves the leaving group falling off. Where SN2, we've got the collision of the nucleophile that's involved as well. So let's make a note of that. Leaving groups are very important for SN1 reactions. And I'll say involved in rate determining step, or RDS. And then we'll compare this to SN2. Leaving groups are only moderately important for SN2, since leaving group falling off and nucleophile are involved in rate determining step. So it's not the sole thing that's determining the rate for an SN2 reaction, but it is in an SN1 reaction, which means it's much more important. All right, so now let's compare some leaving groups. All right, so I'll do an easy one first. First one, I've got an iodine. And then the second one, I've got a bromine. Which is the better leaving group? Iodine or bromine? And why? Once you think you got it, check with your neighbor. All right. Who wants to share their answer with me? Anybody on this side of the room, maybe? We were getting like really left-hand heavy with responses. What do you think, Sean? Iodine, why?
It's the bigger atom, be more stable.
Yeah, so Sean said it's the bigger atom iodine is, so it's more stable with a negative charge. I agree. So iodide is the better leaving group. And that is because I minus is more stable with a negative charge due to its atomic size. Makes sense, right? So if we go down the cardio rules, we know each of the leaving groups will be negative, so it's tied. Then we look at the atom. In this case, iodine is larger. That means it's more stable with the negative charge. So it's the same thing that we did in acid-base chemistry. All right, let's try another one. For the next one, we're going to make a slightly different system. This one's a little bit more complicated. All right, so now what we have to do is we have to compare this green leaving group with this blue leaving group. Which one's going to be the better leaving group, the green one or the blue one?
The green one, resonance.
Green one's more stable because it has resonance. I agree with that. So if we look at it again, the charge is going to be negative versus negative, so it's a tie. If we look at atom, it'd be oxygen versus oxygen with the negative charge, so it's a tie. That means we go to resonance. So this is more stable. Meaning it's the better leaving group since it is stabilized via resonance. So a lot of this is just review of acid-base chemistry that we learned earlier on this quarter. So let's make a note of that. So leaving group stability is directly related to stability of a conjugate base. And let's make a note. Use the cardio rules. All right. So a simple thing you can do is look at a PKA table, and from that you can determine what is a good leaving group and what's not a good leaving group. So I pulled this one from our textbook, and let's kind of take a look at it. So on the top up here, I'm going to just highlight this whole area. These are really good leaving groups because they're really good conjugate bases, right? They're the conjugate base of a strong acid. So good leaving groups are the conjugate base of strong acids. We don't care about solvent that much. We don't care about sterics that much. All we care about is just the overall stability of the leaving group. In general, I define a strong acid as something that has a pKa of less than 0, right? So if you look at the pKa's over here, you notice how they're all less than 0. That means they're really strong acids. If we look down here, at the bottom of the table though, if we get up to like 15 and above, those aren't very strong acids, or at least I hope not. I drink a lot of water. So in this case, OH minus and anything like it isn't going to be a good leaving group. So never kick off OH minus, never kick off a carbon with a negative charge, never kick off a hydrogen with a negative charge. Instead, focus on the conjugate bases of strong acids when you're looking at leaving groups. All of these are crummy leaving groups. So I'll just write bad leaving groups. Make sense? All right. So now I want to give you guys kind of a hypothetical situation. All right, in this reaction, I've got a bromine as a leaving group. I've got sodium iodide. So what's going to be my nucleophile in this reaction? Yeah, the iodide. What's the sodium really doing? It's just spectating, right? So I like to show it because it is there. All right, so do you think this is going to be an SN1 or an SN2 reaction, and why? I'd say SN2, right? First thing I always look at is electrophile. If it's a methyl or primary, it's always going to be SN2. So first step, our iodide's going to hit this back carbon of our electrophile, then kick off our leaving group. All right, I'm not going to show a reaction arrow yet. I'm going to just put a box here. And if this is the case, I'd have iodine here, and then I'd have sodium still spectating, and bromide got kicked off as our leaving group. Do you think this reaction will proceed in the right-hand manner going to the product side on the right?
Nope.
Why not?
Because the iodine with the negative charge is actually more stable than the bromine with the negative charge.
Yeah, so
It's a better leaving group.
just like we did in acid-base chemistry, do you guys remember we looked at stabilities of the conjugate base? This is more stable than bromine, or bromide, I should say. Therefore, our equilibrium arrows, just like with acid-base chemistry, would say because it's more stable, it's really going to prefer the products, or sorry, starting material side over the product side. However, occasionally you can exploit this. And like I said, because it's in equilibrium, maybe we only have 1% of the right-hand side, but that 1% can still do additional chemistry, and we may talk about that later if we have time. But make sure you pay attention to the stability of your leaving groups. It's really similar to acid-base chemistry. All right, so now let's take a look at solvents a little bit. All right, so what about solvents? Let's go back and talk about what we did yesterday. We said yesterday that solvents can be used to help favor a reaction by destabilizing or stabilizing things, right? So solvents can be used to stabilize or destabilize your starting materials, your transition state, which we saw in the pod, and or your product. This can in turn speed up the reaction rate. All right, we said the big thing that solvents do is they lower that activation energy and allow your reaction to occur a little bit faster. All right, so if we're thinking about leaving groups, what can stabilize a leaving group as it falls off? A polar protic solvent or a polar aprotic solvent? We talked about this briefly yesterday. So let me write this down. With leaving groups, the goal is to stabilize them as they fall off. What was that? Just 1 second. I'm like losing my train of thought here. I can only write so fast, guys. All right, so the goal with leaving groups is to stabilize them as they fall off. And what were you saying again, Kisan?
Protic.
Protic? Why is that?
Because it can H-bond as it falls off.
So it can H-bond to your leaving group, which helps it fall off in a more stable manner, right? So H-bonding can kind of catch that leaving group, hydrogen bond it, and then it falls off into a H-bonding shell, essentially. So let's write that down. So polar protic solvents stabilize leaving groups as they fall off through H-bonding. All right, so let's do a little pictorial for this. So I'm going to do a reaction coordinate diagram because I like those. So I'll put reaction progress here. All right. We know that leaving groups matter a lot with SN1 reactions, so I'm going to do an example SN1 reaction where I've got a leaving group on a tertiary carbon, so it's not going to do SN2. It's a two-step reaction, so we're going to go up to this intermediate, and we know this intermediate is going to be a tertiary carbocation, right? And then in the next step, we're going to form our product, which will have our nucleophile attached, right? We said that the rate determining step in this reaction is this activation energy where the leaving group falls off. So let's draw that transition state. And we know in the center, this carbon is going to be partial positive because it's going to a carbocation. And this leaving group, on the other hand, is going to be partial negative because it's falling off. The cool thing with this, though, is this leaving group, because it's partial negative, will coordinate to the solvent around it. Which helps it fall off kind of into a safety net, so to speak. So let's make a note here. So the solvent stabilizes the delta negative on the leaving group. Does that make sense? It's a little bit weird to think about. That's why polar protic solvents are really good for SN1 reactions, because we need that leaving group to fall off in order for the reaction to occur. With SN2 reactions, it doesn't matter as much because your nucleophile matters a lot more, right? Your nucleophile's got to do that first attack before your leaving group gets kicked off. All right, so now the tricky thing is, what if you're stuck and you don't have a good leaving group? What do you do as a chemist if you want a substitution reaction to occur? And there's some tricks we can do. So I've got a whole section dedicated to converting a poor leaving group to a good one. So let's first consider this example. Let's say I have sodium iodide, and I've got ethanol, everybody's favorite alcohol. You could consider iodide your nucleophile just like before, and you could say, well, it's going to attack that carbon, and it's going to kick off the oxygen, right? And I see this a lot where students will say, yeah, why not? Why can't we just have sodium as our spectator, hydroxide as our leaving group, and then a new covalent bond with iodine? What's the problem with this?
OH is a terrible leader.
Yeah. Bad leaving group. That means this reaction simply will not occur because you don't have a good enough leaving group. So we must find a way to convert an OH into a better leaving group. Into a better leaving group. All right. So there's a couple tricks. The first one is protonated. Okay, so let's consider this. Instead of using sodium iodide with our ethanol, what if we use hydroiodic acid? The fastest reaction in chemistry before substitution occurs will always be proton transfers, right? Or acid-base chemistry. So let's do our proton transfer. Our oxygen can grab the proton, kick off iodide. Okay, so now we've got our protonated ethanol. We've got iodide as our conjugate base. Now all of a sudden, this is a good leaving group. And we've got iodide floating around. That can act as our nucleophile. So this iodide can come, attack that back carbon, now kick off the water as our leaving group. And voila, we've got to our final product. So you can do this for some situations. Yep?
I thought iodide was a bad nucleophile.
That's a good point. But if we think about it, right, what's going to be a better nucleophile? Iodide or water? Iodide, because it's got the charge, right? So in this case, you're right. It's not a very good nucleophile, but it's all relative. Yeah. It's a better nucleophile than water. So in this case, it's going to win out. Okay, there are some things to note about this. So I'll write pros first. It's got a high atom economy. But let's write a cons. Can do other acid-base chemistry. In some situations. So, like we saw, this only works well if you only have one group that will do that proton transfer. If you have other groups that will do proton transfers, you might be doing other chemistry you don't want to do. So you have to be very careful when you're throwing acid into a system. So that's one option. The second option is to convert the OH into something else besides water. That's also a good leaving group. So let's make 2 here. Convert OH into OSR, right? This looks a lot like your pod, right? You remember that functional group? You have the sulfur with the 2 double bonded oxygens. These are really good leaving groups. So let's take a look at this type of system. And like I said first, this is a bad leaving group. So our goal is to convert it into a better leaving group, and it's often done with a reagent that looks like this. I'm just going to show you one of them. And really this whole thing is the R group from up here, right? In fact, I'm just going to color code this as R. And this was referred to as tosyl chloride. Chemists oftentimes like to abbreviate this because it's a mouthful, and so you can write this as TSCl, shorthand for tosyl chloride. And in the next step, what they do is they react it in a special solvent. And this is called pyridine, or PYR, shorthand. And all the pyridine does is it acts as a solvent and a weak non-nucleophilic base for the reaction. So it's just helping the reaction to proceed, but not actually doing any substitution in and of itself. When you do this, what you're going to do is convert that OH into a tosyl group. Now all of a sudden you have a good leaving group. Okay, so at that point you can isolate your product and then continue on with it. And you could say, all right, now that I've got this product, I'm going to do a second reaction. But this time I'm just going to use sodium iodide like I attempted that first go around. But in this case it'll work. That iodine can come attack that carbon, kick off your leaving group. We get iodine, still have sodium. And in this case, this leaving group that fell off is actually more stable than iodine with a negative charge. Who knows why? Yeah, it's got resonance, right? If we look at this, we could theoretically say, you know, I can kick electrons up to that oxygen, or I could kick electrons up to that oxygen. It's hugely stabilized through resonance, which means it's a phenomenal leaving group. So quite often chemists will use this as a way of converting an alcohol into a good leaving group. So again, let's make some notes. And again, I'll do a pros and cons list. The pros is it avoids unwanted acid-base chemistry. The cons is the atom economy is super duper crummy, right? We're wasting a lot of atoms in this as our leaving group. So it really depends what your goal is and what the situation is. Both of them can work in simple situations, but if you want to avoid side reactions, you normally go with the tosylation with tosyl chloride. Does that make sense? All right, so now what I want you guys to do is to help me out with this. And I'll give you guys a minute to work on it. But let's say I've got this functional group, an alcohol, and I want to convert it to a thiol. How can I accomplish that? So I'll give you guys a minute to work on that, but try to include all of the reagents you would need along with the appropriate arrow pushing that we just went through. So what should we do for the first step? Ask it nicely to leave. I like that. And what if it says no back to you? You should probably go to the doctor and wonder why chemicals are talking to you. All right, short of doing that, what would be another approach? So we could protonate it. One thing I would say is if you protonate it, you also run the risk of it falling off as water on its own and doing an SN1 pathway. If you notice, we only want SN2. So another way of avoiding that is tosylation to avoid that unwanted potential side reaction. So let's maybe try tosylation first. So for step one, what I'm going to do is I'm going to throw in tosyl chloride and pyridine. All right, when we do that, you can shorthand it as OTS. That TS is basically everything else. Saves a chunk of time. And then in step two, how can I get that sulfur to do only an SN2 reaction there? What reagent should I maybe add in? So do you want the sulfur to be negative? Yeah, I'd say we definitely want a negative sulfur. So I'd say sulfur needs to be negative. We need a countercation. You can pick whatever you want. I'll pick sodium. All right, and if we want it to do SN2, again, we need to be careful about our solvent. Do we want a polar protic solvent or a polar aprotic solvent for SN2? Aprotic, right? We don't want it to hydrogen bond. That means it's going to be a weaker nucleophile if it H bonds. Okay, so what would be a good example of a non-hydrogen bonding polar solvent? What's that? Acetone, right? You guys use that to clean the IR. I like it. So we could throw in acetone, and like we said, this is our polar aprotic solvent. And like we said, this favors SN2 over SN1. And we know we want SN2 because we want that stereocenter to be inverted, meaning it's now a dash instead of a wedge. We don't want two different products out of this reaction. Okay, so now let's go back. Yep. Polar aprotic solvent favors SN2. Yeah. All right, so now let's fill in our decision-making chart since we've covered a few more topics. So if you have that, pull out that chart. We've got our final two rows in here. So the first one's our leaving group. Which one is more important for leaving groups, SN1 or SN2? SN1. So we're at very important. And all right, rate determining step. Okay, so RDS is rate determining step. For SN2, it's moderately important. And that's because the nucleophile matters too. Okay? And then for solvent, right? For SN2, what type of solvent do we typically want to use? Aprotic. We just saw that in an example. So polar aprotic works best. Why is that again? Yeah, because it doesn't hydrogen bond to your nucleophile. That means your nucleophile is less stable and more likely to attack the carbon it needs to attack, right? With SN1, we said polar protic is better. And remind me again why polar protic is better for SN1?
It hopes the leaving group falls off.
Helps the leaving group fall off, exactly. So, I was telling somebody in the hallway earlier, this is the point in the term where students start to feel super duper overwhelmed, and I want you to know that that's a normal feeling. It's a natural feeling. The biggest thing is going through as many practice problems as possible, understanding the why component for everything that you're doing, not brute force memorizing your way through it. And then working in small groups too. When you work in a small group, chances are somebody else in the group will spot something you didn't spot or spot something you didn't think about. And when you explain concepts to one another, that's when things really start clicking in a meaningful way.